Okay, science time. We're talking today about fossils. The fossil record. The objective. Let's do the objective first. The objective reads, and you should write this down. Use fossil evidence to describe Earth's history. Use fossil evidence to describe Earth's history. What's a history? What's an Earth?
It's a big rock.
Okay, great big rock. Yeah, it's more than just that, isn't it? Did you know you're part of planet Earth? You yourself are a part of planet Earth. You know what you're made of? I mean, if you stop to think about it, of course that's true. That what are you made of? Where did the stuff that makes you up, your tummy and your eyeballs and your hair, where did that stuff come from? Earth, obviously. You've probably heard it said that something like the oldest cells in your body are like 3 years old, or maybe your nerve cells are 7 years old. But you're kind of a running average of your components. You're not made out of the same stuff you were last year. So where'd that new stuff come from? Well, it's the food you eat. The food you eat becomes you. And where'd that food come from? The ground, or from a critter that ate stuff off the ground, or from plants that are themselves made of sunlight and oxygen and water. So you are as much a part of planet Earth as a tree is, or a rock, or anything. You are a part of this system called Earth. So Earth is not just a rock. Earth is the system of quite a lot of rock and water and plants and your mom and a Subaru Forester and grass. All that stuff is from planet Earth. It's part of the planet Earth system. And what is the history of that? Well, that's what we're going to talk about today, fossils. That's one of the ways that we learn about the history of that stuff. How do you learn about the history of, say, France? How do you learn about that?
Look it up.
Yeah, you look it up. How do we know that France has a history?
Really old people say so.
Really old people says that. Yeah, the people that were alive in the French Revolution in 1789? 1789? Yeah. Okay. So the evidence we have for like human history is probably, maybe not always oral tradition like Aiden's talking about, where one person passes it on to another, although that's part of it. Probably for things like the French Revolution, let's say, let's specify an event instead of just a location. But for things like the French Revolution, we would probably use writings that were made at that time, right? They would look all fancy and Declaration of Independence, but we would be able to read them if we knew French, and that would tell us what was going on at the time. How do we know about World War II? Well, it's fairly well documented there's articles written about it back then. There is even video evidence of that. How do we know about, let's say, the pyramids of Egypt? Well, that's a little bit trickier because they're quite a lot older than either of those other two things we talked about, so we have to use different kinds of evidence. Can we use writings about it? Yeah, the Egyptians had a writing system, so we can use some writings about it, but they're not overly abundant. I mean, we don't have nearly as many writings about the pyramids, I would warrant, as we do about the French Revolution that are from that time. So the point I'm making is that the further we get back in history, the harder it is to know things. So what about prehistory? How do we know about the history of planet Earth like this? How do we know about prehistory? Before human beings were actually recording what was happening, how do we know about things that happened 65 million years ago when there were dinosaurs? How do we know there were dinosaurs? That's fossils. That's what we're talking about today, is fossils. Evidence of what? Life. Yeah, of past life. A fossil has to have been a living thing. It doesn't have to have been part of a living thing, but it has to provide evidence of a living thing. We call the whole idea of using fossils to tell about history the fossil record. You know, like you would have, like those records from the 70s of female track athletes that are on the hall out here, you know? And this says like shot put Tandy Rising. I don't know. I walk by it all the time, and I probably could memorize the people on there, but that's not super important to me. But those are records. Those are preservations of history, if you will. Kind of like those writings about the French Revolution would be a record. So we call it the fossil record because it records Earth's history through the use of fossils. And fossils are evidence of past life. Fossils are some evidence. It doesn't have to be of the organism itself. It doesn't have to be of its physical body, but they're evidence of life in the past. Let me rewrite this word past. Someone said they can't read cursive in here. It doesn't matter to me who, but maybe I'll try not to write in it as often. Evidence of past life. So fossils are evidence of past life. How do fossils form? What if, I use this example a lot. You guys hunt? Has anyone ever hunted? Give me an animal you've killed. Provide me with an example of an animal you have killed. Okay, Joe killed a deer probably a week ago.
No, I didn't.
So let's say, let's say a stray dog is running across the football field. Ah, there it is. Look, there's a stray dog running across the football field.
Oh gosh.
Oh gosh. Okay, now let's say Joe, because he's kind of a redneck, we've talked about this before, Joe just blasts it. You can't have a gun in school, but Joe just, the stray dog is gone. Rednecks do that just to, I guess, target practice. And now let's say the dog is dead right there on the but unlike what would happen in reality, no one picks it up. No human being touches it. Mr. Van Beek doesn't run it over with a lawnmower. He doesn't put it in the trash can. He mows around it. We just leave it. No human being touches that dead dog. If we come back in 1 year, what do you think will be left?
Bones.
Wrong. Everyone always says that. You're wrong.
It'll be slightly decomposed dog.
It takes 7 years to decompose.
No. Nothing. There will be nothing left. I guarantee you. If we had a dog just sitting out there in the open that was dead, and then we came back a year later, there would be nothing. The eyeballs and the liver and the spleen and stuff like that, the birds are going to get right away. Over time, a coyote is going to come in and tear apart the limbs and eat the meat off of it, probably drag the whole thing off. I'm telling you, as basically a matter of fact, that if we came back a year later, there would not be any remains of that dog there. So then how the crap, no, don't say crap in the video. I'm sorry, YouTube viewers. How the darn do we ever get fossils? If what I just said is true, which it is it possible there might be something left of that dog? Maybe it's possible, but it's very, very unlikely. So how do we ever get fossils? How does something ever get fossilized? Necessities of fossilization. It's kind of special. In fact, it's really quite special. If you think about how many, not just human beings, although human beings are them, but how many critters are alive today, it seems like it must be very special for something to get fossilized. It is very special for something to get fossilized. Most everything, more than 99% of things that die with no record, like that dog, just gone. It would be gone even in a year. So what about 10,000 years later or a million years later? How do we ever have, it's very special. It's very special. Usually, it has to be what? If you've read your explorations, if you've done your explorations, what usually does it have to have happen? Did you do your explorations? I graded them. They were done. Yeah.
Yeah, that was a long time.
What's one way an organism can decompose as fast? You have you ever been to the museum at Fort? Either 100% of the time. It's not like we need usual helped by burial. Cold place. Then meat out on position. chemical and biological. Those processes occur more slowly in the cold. So low decomposition. What else? What else does burial do? Protection from,
Outside things.
be more specific.
Other organisms.
Let's put scavengers. But you're right, other organisms. Organisms that would tear its limbs off, eat its fur, eventually eat its bones. You know, bones. You know that? All the little woodland creatures from the princess movies, if they get a chance, they will eat a bone because the bones are high in calcium, as you already know, because you remember that milk helps build your strong bones and teeth because it has calcium in it. Well, those critters in the forest, they eat bones so that they will gnaw on them like a dog gnaws on a bone. Organisms like to eat bones because it helps them with their calcium. What about if it were, instead of buried, what if it were underwater? That might help. Are there other ways? What's another way that we can have a fossilized organism that actually preserves it really, really well, even its soft parts? Do you know, like from Jurassic Park?
Ice.
No? Okay, ice does work, but okay, we could put ice up here.
Amber.
Amber is what I was looking for, which is hardened resin. I'm going to put hardened tree sap. Sticky old tree sap. If something gets stuck in that, and that tree sap hardens, well, then it's stuck in there for it can be stuck in there for millions of years. Your book enumerates some of the ways of fossils, and I'm going to talk about how these relate to your lab. You can pause it and read that. And when I say your book, for you guys, it's your explorations. But one thing that can happen with fossils, or one way that fossils can be preserved, is called permineralization. This is probably, for the oldest fossils, this is probably the one we see the most often, permineralized fossils. And from your lab, who did a lab on permineralization? That was you guys. So would you explain to me real briefly, how does permineralization work?
Sediment, it like fills in things.
Yeah.
And it hardens.
Yeah, exactly right. So every living thing, we're talking about living things here, but everything has pore spaces. Every living thing has pore spaces. Even in stuff that we think of as hard, like bone, if you look at it microscopically, there are little pores. It's porous. Absorbent and yellow and porous is he. Who's that? No, who's absorbent and yellow and porous? Bob L'Éponge, yeah. Bob L'Éponge is absorbent and yellow and porous means that he has holes in him. And so these holes that are even in bones, they're not that big, obviously. I've enlarged this to show texture like the cereal box does. But those bones, when it's buried, this is all sediment, right? It's buried in sediment. The little holes in the bones, or whatever, could be bones, could be an eyeball, could be in the best cases, it can be an entire nervous system. But these bones get filled with sediment. And then over time, just like my dog on the football field, the thing itself, the actual organism, decays. It decomposes. Hey, that's the whiteboard. Excuse me. I thought that was the whiteboard. So now, I've tried really hard to make it so all the purple that was the original bone is gone, but you can still see that the sediment now is in the shape of a bone. It's not going to be perfect, but it's roughly in the same shape as the thing was before. That's permineralization. So when you go to the Museum of Natural History at Denver, or you go to the Fort Robinson Museum and see those mammoths, what looks like a mammoth, it's the shape of a mammoth, or a Tyrannosaurus rex, or a plesiosaur, or whatever, but it's actually rock. This is the stuff making this up is rock. This is literally a rock. It just is in the shape of a bone. I was going to say it just so happens to be in the shape of the bone, but it doesn't just happen. It happens because it was filling in the holes that were in the bone. That's called permineralization. Carbonization is another one. Carbonization, I think, who did one that was kind of like carbonization? Was that you guys did one that was like carbonization? What did you do? How did you do that?
Well, we did the layers.
Oh yeah, yours was layers. Someone was going to do carbonization.
I think it was this.
Was it you, Tristan? What did you guys do in your lab?
We did a model of how long and stuff for a fossil to become a fossil.
Oh, how long it takes for a fossil to become a fossil. Well, yeah, okay, let's talk about carbonization. Then to be carbonized, usually it happens to fish and leaves because they're kind of flat-ish, but effectively a fish or a leaf lands on some sediment, and then more sediment is piled on top of it. And then over time, the more and more sediment squishes down the fish or the leaf. It can be other things, but you see it most frequently in fish and leaves. And as it squishes down those, it presses the juices out of the fish or the leaf, and it causes a little film of carbon to be there in the shape almost like a stamp. Almost like a stamp. I'm trying to think of another way we could think about it. Yeah, if you had like, you know about stamps. I mean, I don't mean like the stamps on a letter. I mean like the rubber stamps where you put them in ink and then you put them on a piece of paper and you can see the outline of the thing. It's kind of like that, except
It's mostly rock and it's just the outline of it. Like,
yeah. So this would come out. What we would see is a chunk of rock that it had like. It looks almost like a drawing of a fish or a leaf or something on it, or it could be other things. But fish and leaves are most common because they're flat. There is one. Yep, I bought one from the Rock Swap a couple years ago to show people carbon film. We've talked about amber, casts and mold. Who did one with clay? I think someone. Did you guys do one with clay too?
Plaster and filled it.
Okay, yeah. So a cast and a mold. We'll talk about these in two separate ways, but a cast and a mold. A mold is the imprint left. So if you had a piece of clay and you stuck, I don't know, this dry erase marker lid in the clay, it would leave an impression. It would leave a negative impression. Everywhere where there was a hill on this lid would be a valley in the clay, and everywhere where there was a valley in the lid would be a hill in the clay. I'm using kind of chaotic words, but you understand what I mean. Like where the hole, there would be a positive thing. That's called a mold. So if we had, the mold is the negative impression of it, and then a cast is when that gets filled in. If we fill this in, let me make the word cast brown. If that gets filled in with some other kind of sediment. So the organism gets squished into some soft sediment, the organism decays again, and then new sediment comes in and fills in the hole where the organism was. Well, now the new sediment is a cast. So the mold is the sediment that was there that the organism got squished into, then the organism decays, and then the new sediment that fills in that hole is a cast. And the cast will have the same shape as the organism did. It will be a hill, and a valley will be a valley. Your book also talks about tar pit fossils and frozen remains, but both of those are what fall into the category of original soft parts or original hard parts, where instead of, so this one's a rock, this one is just carbon in the shape of the organism, God bless you, and this one is rock, but then we also have original hard and soft parts. Oops, sorry, original hard and soft parts. So, original meaning that it's the actual stuff of the organism. So if somehow, because of a burial maybe, that dog out there didn't die, didn't decay, it did die, it didn't decay, and we came back 500 years later and there was an actual bone, not a rock in the shape of a bone, but an actual bone, that would be an original hard part. If, very, very unusually, there was an actual eyeball, that would be an original soft part. You know the difference between hard and soft part. What are the hard parts of the body? Bones and? Teeth and maybe claws, depending on the organism. And then the original soft parts would be things like guts and skin and fur and feathers. And that's very rare. The only time that I can think of that we find original soft parts from any fossil of even somewhat significant age is in amber. Maybe in tar, maybe frozen, but usually just in amber. So these kinds of burials lead to these kinds of fossilization. And then there's also this distinction between body and trace fossils. So body fossils are the actual, they don't have to be the actual original hard parts, but they give us an indication of how the organism actually looked. Fossilized parts. And the trace fossils are, in a way, fossilized behaviors. They tell us how the organism acted. Things like footprints, things like eggs, things like nests, things like poop, which we call a coprolite. A coprolite is fossilized feces. Poop. So what do we do with fossil evidence? It's neat. It's cool to go look at fossils, right? Is it useful? Yeah, is it useful for telling us about Earth's past? Yeah, and one thing is, I'm going to erase this middle bit because I think we've already got it, but one thing is it tells us not just about the actual organisms themselves, it tells us about how planet Earth was. For instance, if we find a fossilized organism that has a lot of fur and it's pretty big and stocky, and there might be evidence that has a lot of fat, what could we infer about the climate? Not always, but what could we make a reasonable inference of the climate? Probably a cold climate. If we find trees that are not palm trees, but they look kind of like palm trees, they have broad leaves, very little serrations, they don't have a waxy coating, what could we infer about that climate from that tree? Probably a warm climate, probably a warm, humid climate. So we can make inferences about the Earth itself from the fossils. We use these fossil evidence not just because they're cool, but because they tell us about how Earth used to be. One way we do this is let me tell you too. We have relative dating and absolute dating. Sometimes called absolute age dating. Relative dating is when you see a cute girl at your family reunion and you're like, no, Joe, I'm just kidding. That's just a silly joke. That's just a joke. It wasn't Joe. Joe would never do that. You get my joke, though. Cameron, I thought you'd think that was funny. Relative dating. Ha, 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 ha. No. What does relative mean? Sure, it's people related to you. What does relative mean? No, let's use it. Relative means compared to. So these people are relatives of mine because compared to me, they are my cousins or aunts or siblings or whatever. They aren't yours. Compared to you, they're not your parents, right? Relative means compared to. So an example we often use for this is that relative dating is like if we had, instead of relative dating, if we had relative height, we might say Tristan is shorter than Cameron, right? That would be relative height. Now, it's not. Tristan is 5'3", and Cameron is 5'9". Those would be absolute heights. Those are heights that are measured in units. That's an absolute thing. Relative is comparing. So in this one, we're comparing, and this one we're telling numerical, like referring to numbers, age. So in this one, we're comparing. We're not saying this fossil is 36 million years old. We're saying this fossil is older than this other fossil, or this rock is older than this other rock. And for this, we use what are called Steno's principles, named after a man called Nicholas Steno. A Dane, I think. Steno's principles. One of them is superposition. You remember from your explorations what superposition is?
The way that it states that the farther down in the earth you go, the older.
Yeah, generally, and that's what your lab was about, right, Streety? Generally, the oldest rocks, the oldest fossils, the oldest stuff is on the bottom, and newer stuff is on top. Who has a pile of laundry in their room? Who has a pile of laundry in their room? Who has a laundry basket in their room? Where are the oldest, crustiest socks in your laundry basket? At the bottom, because they've been in there. Like since the time your mommy dumped it out, the ones that were in there first are now, by now, the oldest. Maybe those are 2 weeks old, maybe they're 2 months old, I don't know your life. But the ones that are generally, unless what? Is it possible for you to go into your laundry basket and be like, jumble stuff up?
Yeah.
Sure, but it takes energy, and that would be unusual, right? So generally, the oldest layers of stuff are on the bottom. That's superposition. Oldest stuff on the bottom. That's superposition. Is it possible that is undone? Sure. We often say in an unoverturned sequence. And a sequence is like a series of layers of rock. But in an unoverturned sequence, in a sequence where tectonic activity or faulting or whatever hasn't flipped it over, the oldest rocks are on the bottom. That's unoverturned. Absolute age dating tells us the numerical age. And the numerical age is usually found with radioactive isotopes. Basically, some elements, which are found on planet Earth, decay at a known rate. And they decay into a known thing. So, for instance, there's a question here about thorium-232, a specific isotope of thorium called thorium-232. Has a half-life, it says, of 14 billion years. So if we look at a rock that we find on planet Earth, and we see that there's a certain ratio of thorium to whatever its daughter isotope is, whatever it becomes when it decays, that we can tell how much time has passed. So maybe, since the half-life of this, which is indicated by the Greek letter lambda, equals 14 billion years, 14 gigaonnum, we'll talk about that when we watch our little video, and we see that maybe a third of a half-life has gone by. Well, that means that that rock is about 4.5 billion years old. So we use these known things that have a known half-life. And how do we know the half-life? Well, we can measure it in a laboratory. We can have a chunk of thorium-232. We can see how much radiation is coming off of it, and we can measure how long it would take for half of it to decay. There are all different other things. It's not just thorium-232. We also use uranium-235, 238 maybe. We use zirconium. We use bismuth. There are all different kinds of radioactive isotopes. A lot of times we use strontium or potassium. Those are elements that we find a lot in rocks. And that tells us how long those rocks have been since they were magma. When they're magma, the rocks separate out into these different elements. And so by looking at the rock, we can tell how long it has been since that rock was magma. So basically how old that rock is. And by using that in combination with this, we can say things like, we know that the dinosaurs lived 65 million years ago, for instance. And when I say no, I mean all the evidence suggests that that is the case. Some fossils are better than others at telling us the age of things. When we're looking for fossils to tell us how long something has been around, we use what are called index fossils, which we really want to be worldwide, Mr. Worldwide, and we really want them to be common so that lots of people can find them, and we really want them to be short-lived. Why would we want that organism to be a short time between when it rose evolutionarily and when it went extinct? Why would we want that? No, I don't mean the organism itself. I mean that species went extinct very soon after it arose in the geologic record. Why would we want that? Why would that be beneficial? It's pretty clear why worldwide and common are nice for index fossils, for us to tell the age, because we want to be able to tell about the age of that rock all over the world, and we want it to be lots of different places so that we can find it pretty easily.
So we can know what time.
Yeah, if it lasted for a long time, if it lasted for 100 million years, well, finding that fossil doesn't really narrow it down much. We can only say, like, well, this rock is between 200 and 100 million years old. But if it only lasted for 1 million years, well, then finding that, we think, oh, wow, we know this rock was 98 million years old, or whatever. Do you see what I mean? The shorter lived it is, the better it narrows down how old that rock might be. Do you see how fossils provide evidence for not just past life, but for Earth's history? Do you see how we can learn about Earth's history from fossils or using fossils? Because remember, we can't go back in time. I mean, I shouldn't have to tell you to remember that. You can't go back in time. Whatever mistakes you made yesterday or whatever, I don't know, whatever embarrassed you on Snapchat, I don't know your life, whatever mistakes you've made, you can't go back in time and correct them, right? You can't go back in time. And so we can't go back in time and be like, oh, neat, we can see the dinosaurs walking the Earth. All we can use is the evidence that they left behind. And we can use that almost like a logic puzzle to say, well, we know this, and we know this, and we know this, and so the truth must be somewhere in between these three things. Questions? Questions, Cameron?